Wind turbines look simple. A tower, some blades, spin in the wind make power. But if you've ever looked at the data behind one of those machines, the picture gets complicated fast. Each turbine is constantly dealing with variables: wind speed, wind direction, air density, blade pitch, temperature, vibration. And those variables change second by second. For decades, operators managed all of this with fixed rules and scheduled maintenance. You check things on a calendar, you adjust settings based on averages, and you hope for the best. Now AI is changing that, and the results are genuinely impressive. Here's the basic problem. A wind farm isn't just one turbine. It might be 50, 100, sometimes more. Each one sits in a slightly different spot. The turbine at the front of the farm catches clean, fast wind, but the ones behind it catch what's called wake turbulence. That's the messy, slower air left behind by the first turbine's spinning blades. It's less efficient, and it puts more stress on the machines in the back. Traditionally, every turbine just ran at its own optimal setting, ignoring what the others were doing. That made sense when you didn't have the computing power to coordinate them all in real time, but it left a lot of energy on the table. What AI brings to this is the ability to think across the whole farm at once. Instead of each turbine chasing its own best output, the system can slightly adjust the angle of the front turbines, intentionally deflecting their wake so it hits the back turbines less directly. The front turbine gives up a tiny bit of efficiency, but the ones behind it gain more than that. The farm as a whole produces more power. It sounds like a small tweak. But across a large wind farm, over a full year, that kind of coordinated optimization can translate to millions of additional kilowatt hours. That's real energy that didn't exist before, without building a single new turbine. And that's just the aerodynamics piece. AI is also being used to predict when things are about to break. Wind turbines have a lot of moving parts under a lot of stress: gearboxes, bearings, blades, generators. When something fails unexpectedly, you're not just looking at repair costs. You're looking at downtime, crane rentals, and sometimes dangerous conditions for technicians working at height. Predictive maintenance changes that equation. Sensors inside the turbine are constantly feeding data into a model that's been trained to recognize the early warning signs of failure: a slight change in vibration frequency, a bearing running a few degrees warmer than usual. Patterns that a human analyst might miss or catch too late. The AI flags it early. The operator schedules maintenance before the failure happens. You swap a part on your schedule instead of scrambling in response to a breakdown at 2 in the morning during a storm. That's not a hypothetical. Wind operators who've deployed these systems are seeing real reductions in unplanned downtime, and in an industry where availability directly equals revenue, that matters enormously. There's another layer to this too, and it's about the grid itself. Wind is intermittent by nature. It blows when it blows. Grid operators have to balance supply and demand constantly, and variable generation from renewables makes that harder. AI helps here by improving forecasting. Models trained on weather data, historical output, and grid conditions can predict what a wind farm will produce hours or even days ahead with much better accuracy than older methods. That gives grid operators more confidence, and more confidence means they're willing to integrate more renewable capacity without worrying as much about stability. So better AI forecasting actually helps unlock more wind investment. It's a compounding benefit. Now, this isn't all frictionless. Deploying AI in industrial settings is genuinely harder than it sounds. The data can be messy. Sensors fail. Turbines from different manufacturers produce data in different formats. The models need to be robust enough to handle edge cases without making a bad decision that damages equipment or causes a safety issue. There's also the human side. Experienced turbine technicians have deep intuition about these machines. Getting them to trust an AI recommendation, especially one that says, slow this turbine down a little so the ones behind it do better, requires building that trust over time with real results. The technology has to prove itself before it gets handed real responsibility, but that trust is being built. Companies are running these systems in parallel with human operators, showing them the AI's recommendations alongside the outcomes. When the model's predictions keep proving accurate, people start listening. What's striking about all of this is how invisible it is to most people. When you hear about AI breakthroughs, you usually hear about a chatbot writing poetry or an image generator making art. But some of the most meaningful AI work right now is happening in places like this. Out in a field somewhere in the cold on a wind farm, where a model is quietly deciding that turbine 12 should yaw 3 degrees to the left so that turbines 13 through 17 can breathe a little easier. That's not glamorous, but it's real. And at a moment when the world is trying to generate more clean energy without building more infrastructure than it has to, getting more out of what's already, there is exactly the kind of problem AI should be solving. The turbines are already out there. Now we're finally teaching the software to run them properly.